Yeah. Yes.
Good to meet you.
Did it?
Josh was like,
But
We
I
got it.
wanted to.
we had like.
Oh, you're here. Thanks for coming. All the way from, okay, we're live streaming and I guess that works.
So we are live streaming now. Okay, very good.
Yeah, but I'm gonna move this back a little further.
Carry cords so that
Because of the angle. Huh, okay. Might be all backwards.
If you go any further
Yeah, but-
back, it's gonna be too tiny.
I'm thinking of
Turn it
using a
around and use
textbook.
the front cam, the
Yeah,
textbook thing.
Yeah.
There's the textbook drop thingy.
Oh yeah, and then we can raise it.
there are always technical challenges with any talk. But
The external.
this is actually a really nice thing to actually try to live stream the talk for the external, which we don't normally do.
Why the mic would be better?
The mic will be up there, but
Yeah,
it's just
great books. Wow.
We can lose the keyboard.
you
If we
lose the
can.
keyboard. So I'm just gonna have to hope that that it's set not to go to
Okay, we
sleep.
need higher. We need more books.
And you'll have to move because it's gonna be right in your way.
I'll just look through it. I get my own like zoomed in version. Well, I guess zoomed in version.
Are you recording it for?
It's live streaming. It'll be live streaming, but not recording, I don't think.
It will record at the end, so
Oh,
we will
excellent.
have the record a record of it. Can you hold this, please?
You can show your kids. I did. Back in the day.
Back in. Yeah. This is backwards.
It used to be.
Oh, it's gonna cut off or should we move it closer?
The only other thing, like a very delicate sort of think you should set like something just in front and just
Mhm.
behind it so that it's not gonna take off at some point.
Well, I was hoping Rob would sit here just to
Oh,
make
and just
sure.
hold it,
Do
yeah.
you want me
maybe.
to take care of it?
Let's check something.
Find a way to use the camera in the front. Probably could be.
Yeah, does it have, it has a front camera, doesn't it?
It does, yeah.
Maybe if you flip that around,
The kickstand works in your favor at least.
yeah.
Well, I don't think I could change it on this.
Work at it. Go to the gym today. 6 in the morning.
I was here that long.
So I hope you're all watching this the time my milk is comes around.
I'm going to live stream by.
I have a better solution.
Wow.
Because this has cords on it as well. Plug it in. And it's not very-
He is not. Under that table.
Well, is it likely to block everyone's?
Well, yes, but they can move. So. There. I'll let you adjust. I actually got here at 8 o'clock. so that we could do all the setup.
We need
but I
something
left my computer at home.
Maybe if I could say, if you put books behind it,
Yeah, I
you
did.
can crank the angle
Yeah.
up more.
All right. Bless you.
There you go, that's good.
Now, there is a
Perfect. Look at you go.
plug in somewhere in here. Oh, there it is. And the plug out
There's no way.
was here.
You can see it through there.
What does it say?
You got on this list. Algebraic companions and linearizations. Eunice Y.S. Chan.
While I am trying to untie this cord, I will do the introduction. Everybody here
Prescriptions as well?
knows Eunice. But people who view the record of this interesting setup, let me get a knife, I'll cut this blasted tie here.
Here's the university.
Oh, there we go.
Did you hear about the Polish man that went to get his eyes tested? And the doctor said, "Can you read the bottom line?" He said, "Read it, I know him."
It's a very sad joke.
What is Polish? Too early?
Yep. Too early for Game and Jeffrey jokes. I still wish I
hope we can trim this,
story so I could retell
recording.
the avocado story. Because I don't remember how it went. It was something about an interportant avocado, and I wish I knew it because it is the best story I've ever heard.
I must have made it up on the spot.
All the fuses go.
All right, the whole room goes dark.
This marks the official start. This is still recording nicely? There.
Looks like it.
Okay.
Tyler, you're responsible now. If it
All right.
stops.
If it stops, how do I know if it stops?
How do I
No,
know
it
it's
doesn't
recording
have like
properly?
the live.
Are you live streaming on
This is live
YouTube?
stream.
Yeah.
Yes. This is live streaming on YouTube. And then she'll
So I can send the link everywhere? Everybody watch this.
Okay, welcome to the PhD lecture of Eunice Chan. Eunice has been a student here at Western for a long time. She came to do her undergraduate and then started working with me with her honors thesis project after taking some courses with me, numerical analysis and then experimental mathematics. Her undergraduate thesis got turned into her master's thesis, rolled in as they do, her master's thesis on Mandelbrot polynomials, solving Mandelbrot-like polynomials with homotopy methods and matrix methods, has generated a number of interesting papers. It led very naturally into her PhD work. So Eunice has now been working on her PhD for 3 years, which is rather more rapid than most of the PhDs in this department, but not all. The current record is held by J.P. Pascal, who did his PhD in 22 months. So this should be inspiring for all of you in the audience who are thinking about doing your PhD on fast mode, but 3 years is still very fast. So Eunice is going to tell us about algebraic companions and linearizations. A lot of this work was done in Spain in the last little while, and she will tell us all of her adventures. So.
All right, thank you so much for the introduction, Rob. I'm very happy to be presenting what I've been doing for the past 3 years, and thank you everyone for coming. So, an overview of what I'll be talking about today. So in the introduction, I'll be talking about kind of an overview of what I did during my master's, just very briefly, just kind of as a motivation as to why we're doing the rest of this. In the second part, I'll be talking about one of the papers called Minimum Height Companion Matrix for Euclid Polynomials. And it is an extension of what I'll be talking about in introduction, and in the rest of these from part 3 to 5, now we're dealing with matrix polynomials rather than scalar polynomials. And here in algebraic linearizations of matrix polynomials is an extension of the generalized theorem presented in part 2, and part 4 and part 5 are pretty much additional information for part 3. And lastly, there are some concluding remarks in future work. So for introduction, let's talk about what a companion matrix is. So let's just say we have P of Z, which is a scalar polynomial, and by definition, the first Frobenius companion matrix is as follows. So we can see that below in the bottom line here, hopefully the people behind the whole setup here can actually see the bottom line, but the bottom row of C1 are the coefficients of this matrix. But we'll notice that this one here, it does not appear in C1. And this is because it is a monic matrix, so by definition, we have this. If, by chance, if this is not equal to 1, either we could divide everything. If this is not equal to 1, the coefficient of it, we can either divide everything by Cn, or we could create another matrix, which I'll show much later. And yeah, pretty much. Here only applies for monic matrices, polynomials. And if we take the characteristic polynomial of C1, we get P of Z back. So all of this began with matrix polynomials. So by definition, we have the recurrence relation P0 equals 0, Pn plus 1 equals times Pn squared plus 1. And here below, I just give you the first few expanded in the monomial basis. So Rolf's former PhD student, Piers Lawrence, actually, I guess, either invented or discovered another way of expressing a companion matrix for these particular families of polynomials. So if we let Rn equal a vector with zeros, and then the last element here is 1, and Cn is a column vector with the first element as 1, and the rest are equal to 0, and both of their lengths are dn, which is equal to 2t dn minus 1, which matches the degree of the corresponding polynomials. So here we have the construction. So we're using the previously known or constructed matrix polynomial, the companion of that, and placing it on the top left and the bottom right. We're gluing everything by these vectors that I talked about earlier with the minus Cn times Rn over there. So here is the construction. I'll go over the proof very shortly. But the reason why we're interested in these particular matrix polynomials, companion matrices, is that if we took the time complexity experimentally of these particular, when computing the eigenvalues, we can see that the slope of this is less than the slope of this. So normally, when we are computing eigenvalues, we expect the time complexity to be of the order n cubed. But in this case, we see that our time complexity is around order n 2.3, which is what I calculated there. So due to the upper Hessenberg structure, as we saw previously, so here would be upper Hessenberg, and it would be sparse, but I don't show you that sparse. We see that because of those two factors, the time complexity is less than what we expect. So the general theorem, so A of z, let's just say that we have a companion for that, and we have a companion for B of z. It doesn't necessarily have to be matrix polynomials now, it could be for anything such as Mariana-Mandelbrot polynomials, Fibonacci-Mandelbrot polynomials, which I discussed in my master's thesis. We introduce alpha, which is 1 over the product of the subdiagonals of A and the product of the subdiagonals of B. And that falls here. And I guess I should talk about the dimensions. So D of A should be equal to the degree of A of Z, or the dimension of the companion matrix, and same as B. And we can see that we have A and B in the top left and bottom right areas of the matrix. And if we remember back for the Mandelbrot matrices, we recall that both of these are the same, and they are in the same position. And we have the row and the column vectors, and here is still the same. We introduce the C0, which is here, and the alpha, which essentially gives us the negative or the positive one here in the top right corner. And if we take the companion matrix of that, we get Z times A of Z times B of Z plus C0. So this particular form is what we are focusing for my whole entire thesis. Because not only do we use this form for our scalar polynomials or companion case, we also use this for our matrix polynomial case. So let's first talk about minimal height companion matrix for Euclid polynomials. So this is an extension of what I just talked about. So let me introduce why or how the Euclid polynomials are first made, I guess. So we have the sequence, which we can find in the OEIS under this code. And we have the sequence 2, 3, 7, 43, 1807, so on and so forth. We notice that this can be made by the recursion that's shown here. So we start with E1 equals to 2, and for our next one, we are multiplying all of the terms before in the sequence plus 1. So we can see that it works for E2, so it will be 2 plus 1, so it will be 3, and then for E3, it will be 2 times 3, which is 6 plus 1 equals to 7. So the history of Euclid numbers comes from Egyptian fractions. So the greedy Egyptian representation of 1 is equal to, so 1 is equal to 1 over 2 plus 1 over 3 plus 1 over 7, so on and so forth. So we notice that the denominators of each term are the sequence, or is in the sequence of the Euclid numbers or sequence. And algebraically, we can show that 1 is equal to the sum of 1 over EK, and then plus 1 over E plus 1 minus 1. So just a note, the sum only is for this term, it doesn't include this term, if anyone is confused about that. And we can show that this works simply because we know that the the product of all of the previous terms is equal to En times En minus 1. All right, so now we go on to the Euclid polynomials. So we take the same idea in which we are multiplying the previous terms, but instead of terms, now we are talking about polynomials. So instead of E1 equals to 2, we now start with a polynomial lambda plus 1. And similar to how the recursion works for the Euclid numbers, we have lambda times all of the previous polynomials plus 1. So we can draw some parallels to this particular equation or recursion to the Mandelbrot recursion. So in the Mandelbrot recursion, we have z times pn squared plus 1, but now we're just introducing more terms that we're multiplying in the first part of the recursion. So to show you the first few, we expanded out in the monomial basis. We can see that for at least these ones, that all of these coefficients are positive, and we can see that the degree is growing exponentially. So now we're talking about the companions, and here we can see some sort of similarities to this polynomials and the Mandelbrot polynomials. So in this case, so we're starting with E1 equals lambda plus 1. So obviously the solution to this is lambda equals minus 1. And therefore the companion is just simply minus 1. And we can take the companion matrix, we can see, great, we have the correct solution. All right, so now we're moving on to E2, and as we can see that this is lambda plus E1 plus 1. And to construct the companion matrix, we first looked at it in different parts. So the lambda, that is highlighted in red, corresponds with the 0 in the top left corner. Then the minus 1, since it's a solution to the lambda plus 1, falls in the bottom right corner. We glue everything up with the minus 1, and the 1 over here is 1. In the Mandelbrot polynomials, or the Mandelbrot matrices, this term is always minus 1. However, for the Euclid polynomial case, that's not always the case, because the 1 here, the sign of the 1, depends on the degree of the polynomial. And if we take the characteristic polynomial, we get exactly the same thing as the polynomial. And here we show for E3 and E4, and we notice that we always have the 0, E1, or the companion of E1, the companion of E2. And here we can see in the block diagonal is the same thing, 0, the companion for E1, the companion for E2, the companion of E3. So we can see that for any Euclid matrices, we would take the previous companions and put them in the block diagonal. We glue everything with minus 1, so we're putting them right in the corner here. And here it would be 1, depending on the dimension of the matrix. So as I just mentioned, 0, E1, E2, so on and so forth. We glue everything with minus 1, and we put a 1 in the top right corner. So some reasons as to why we're interested in this particular construction. So there's a massive reduction in height. So we notice from here that all of the elements are either 0, minus 1, or 1. So if we take the condition number of these matrices, it would theoretically be much lower than if the matrices were full of numbers that have a magnitude greater than 1. Not only with the condition number of the matrix being much better, it also makes the eigenvalues much easier to compute because of the stability of the companion. As I mentioned, numerically stable results, and we can extend this to the matrix polynomial case, which I will be talking about very soon. So here we have the roots of these polynomials, just so that you can see some pretty pictures. Here we have 2 roots, 4 roots, and we can see that by E10, so the 10th Euclid matrix, we get this cauliflower shape. Now we want to look at the condition conditioning of the eigenvalues, because previously I claimed that these companion matrices are numerically stable and they are very well conditioned. So let's actually show you that it's pretty well conditioned. So let's define what a pseudospectrum is. So here we are taking the norm of the inverse of Zi minus Ek, which is greater than 1 over epsilon. But instead of calculating the pseudospectrum like this, I usually calculate it using the SVD, simply because it's much easier. And it's more traditional to use that one. And to compare the pseudospectrum, which essentially tells you the nearby solution. So if you perturb your problem a little bit, you want to make sure that the solution to that is close to the exact one. So that is the definition of well conditioned. So you find the exact solution to a nearby problem. That is the definition, or the same idea for a pseudospectrum. So you're perturbing it, and you're perturbing it to an amount that you are setting, and you can see the difference between the results of the result, the perturbed result, and the exact result. And then for pseudo zeros, so this is no longer for the companion matrix, but rather the polynomial itself. So here we have the absolute value of the polynomial, and it has to be less than epsilon, so a small perturbation, epsilon, and the condition number, which we define as E of k of absolute value of lambda. So usually, the condition number, we would have to take the absolute value of both the coefficients and the the lambda or value. But since, as I mentioned before, the coefficients of the Euclid polynomials are all positive, then we don't really need to worry about putting absolute values there. So let's take a look at some more pretty pictures. So first, let me explain that this, the left figure here are the pseudo spectras, and the right figure here are the pseudo zeros. So just to make things clear, this one relates to the companion matrix, and this one is related to the polynomial itself. So also, I should mention the values that are being used. So the more purpley color, so the ones that are more close to the roots, in this picture is 10 to the minus 2, and the ones that are further out from the roots, so the yellow sort of color is 10 to the minus 1, whereas in this case here is 10 to the minus 5, and out here is 10 to the minus 4. So what this already tells you with the numbers is that even though we are introducing larger perturbations for the pseudospectra, the pseudospectra themselves are much more closely to the roots than if we kick it even a small amount. So we can see that just visually, these are comparable in terms of the distance, but then this one, it only takes a really small perturbation, whereas this one, we really need to kick it before it kind of moves from the roots. And in addition, I want to call your attention to here. So we can see that on this particular side, it is less well-conditioned than on this side. And this is basically because, well, if we shifted the whole polynomial by minus a half, then it would, well, a half, so that is centered at 0, it would be much better. Unfortunately, I don't have a picture of this, but it's in the paper. But just to kind of explain how we can tell that this is, well, more well-conditioned than this part is, as I mentioned before, imagine just kicking or perturbing our problem by a little bit. So if we're kicking the problem a little bit, if our problem is well conditioned, then our solution should be very close to the root. So we can see that, for example, the yellow part, we're taking it 10 to the minus 4. And we can see that this doesn't move as much from the root compared to this, where it moves a lot more. So we can see that this part is much more much less well conditioned than this part. Okay, so now moving on to matrix polynomials. So let's talk about PEPs, or polynomial eigenvalue problems. So it is pretty similar to the scalar case, but now we are dealing with matrices as the coefficients rather than just scalars. So similarly, we are trying to find the eigenvalues and the eigenvectors. So the eigenvalues would be the lambdas in this case, and the eigenvectors would be the x and the y star for left and right respectively. I don't know my left and right and left respectively. In this particular talk, we can see that this form appears again. So previously, remember I called your attention to z times a of z times b of z plus 1, or c of 0. Now we have a similar form, but instead of them being scalar polynomials, they're now matrix polynomials. And we denote the dimensions r by r. So the matrix coefficients themselves are size r by r. And we should also talk about the degree, which I have seemed to left out. But I think I talk about that later. Anyway, so to solve these polynomial eigenvalue problems, we use a very common technique called linearization, meaning that we are converting our problem to a bigger problem, like what we have seen for the companion case. So I will show you in a bit the corresponding linearization. So you can think of companion matrix is to scalar polynomials, whereas linearizations is to matrix polynomials. So instead of calling them companions, we just call them linearizations for the matrix polynomial case. Here, the idea of linearization, as I mentioned, is to convert this particular problem to a larger size so that it looks like this. And here, L of lambda is a much larger but linear eigenvalue problem. So let's take the matrix polynomial P of lambda. We can see that is very similar to the scalar polynomial case, but instead here is a matrix. And actually, remember that previously I mentioned that the coefficient of this larger degree was 1? Well, for the monic case, for the matrix polynomial case, this could be the identity matrix, but now we're generalizing it so that it does not necessarily have to be the identity matrix. So here, we are transposing what we have seen previously, but it's pretty much in the same format, where we can see that we have the coefficients laid down in the row. Previously it was in the column, but that's okay. So here we have all of the coefficients except AM, and we have the identity matrix in the sub-block diagonal. And here, previously it was the identity matrix. But then since we are allowing A of M to not necessarily be the identity matrix, let's also restrict it so that it is not identically 0 to make it easier. So here we put where we would put the AM. So let's just say, for example, A of M is equal to the identity matrix, then this whole thing is the identity matrix, and we would go back to our monic case. So we have this, which we call the resolvent form, where it states that the inverse of our matrix polynomial is equal to x times lambda c1 minus c0 inverse times y. And we're just saying that this particular part, the lambda c1 minus c0 is equal to L lambda, and we have their x and y's, and I will talk more about this later, but the x, L, and y is what we call a standard triple. But this is very useful, and this is a very useful property when we want to prove other linearizations. So as I mentioned before, we're interested in matrix polynomials in this form. I just kind of changed the notation, but it's pretty much the same, except for the D0. Typically, we'll just assume that D0 is equal to the identity matrix, but we have generalized this so that it doesn't have to be, and that we would multiply a matrix polynomial by a matrix times a matrix polynomial with a set in front and another matrix. So I mentioned all of that here, and in this case, we are assuming that A of z and B of z, which are both matrix polynomials, have a regular linearization pencil, such as the one that I presented earlier, the Frobenius one. And we can say that and because they have a regular linearization pencil, the determinant of A of z is equal to the determinant of the linearization themselves. And as I mentioned, XA, YA, and XB, B, and YB are the standard triples for A of z and B of z respectively. So our algebraic linearization, so rather than using the Frobenius linearization, we have extended what I have showed you for the scalar case to the matrix polynomial case. So here we have A, which is similar to what I showed you before, and B, but in this case they're much larger in dimension, and here has the resemblance of Rn, here has the resemblance of Cn from before, and here is slightly different, but then this places the C0 in the top right corner if it's expressed in the monomial basis. So essentially the y of A and the xb just moves the C0 around in that block. So here would be our H, so in the previous slide I call it C0, and here for DH we have the DA, DB, which remember is our part of our linearization pencil, and we have the Z0 where the middle part that I was talking about falls in. So usually we'll assume that that is identity matrix. And here we have to use our previous standard triple, so XP to create our XH, and we need to use our previous known YA to create YH. And this gives us the resultant form, which is shown here. So I'm only going to cover part of the proof. I'm not going to show you the whole entire proof. So the resultant form I'm not going to talk about. I'm only going to show you that the linearization gives the same roots as the roots of the polynomial by using the characteristic polynomial. So we are using the Schur complement of block C11, and this is just by definition. We can separate our matrix into 4 blocks, a 2 by 2 block, and we can factor it as such. And what's really nice about this is that if you take the determinant of these two, then it's pretty simple because it's just the determinant of C11 and the determinant of C22 minus C21 times C11 inverse times C12. So breaking this up actually helps us immensely because we don't actually need to go through and calculate the determinant for each individual one, which would be tedious. So by Schur factoring, z times dh minus h to two parts, which I show here, we can see that we have kind of divided it like this. So we can think of this as one block to second block, third block, fourth block, and the same part here. So we can see a lot of things going on. This one's in a really nice form because the determinant of this is just simply the determinant of this upper block, whereas this one's a little bit more messy, so we want to sure factor this again. So by doing that, I just kind of skip a bit of steps and determine that the determinant of whatever we factored here are just simply this one and this one. And by taking the determinant of z times dh minus h, and instead of just taking the determinant of this, we simply use whatever we factored, and we take the determinant, or we multiply all of them together. And we can show that by doing such, we get the determinant of h of z, which is equivalent to z times dh minus h. So we can see that our linearization, the characteristic polynomial is in fact our matrix polynomial h of z. So now moving on to standard triples, which I kind of touched upon earlier. So here, let's first talk about the standard pair. So the standard pair has two conditions. So one of the conditions require that the sum of p of k, which are the coefficients of p of lambda, times x, which is shown before, and t of k, that they're equal to 0, and that we have this matrix, which we're going to call Q, and that is non-singular. So those are the two requirements for us to be able to say that x and t are standard pairs. And I talked about standard triples before, and using the matrix Q that we talked about, we can take the inverse of that multiplied by this matrix here, which has 0 blocks in the identity matrix. And with that, we say that the standard triple is x, t, and y. So if we are dealing with the monic case where the matrix coefficient of the largest degree is equal to the identity matrix, then we get this, whereas here, we just simply call it t. Whereas previously I showed you the generalized case where the coefficient of the highest degree is not necessarily the identity matrix, then we take the whole entire thing and call that the standard triple. So that's the little difference between what I was talking about before and here, because this is just for the monic case. Okay, so now, so essentially in this paper, we are calculating all the standard triples for different polynomial bases. So this is just a universal theorem that we can look at just to kind of hand wave our way, saying that this works generally for any different polynomial bases. So let's just take this polynomial and say that it equals to 1. So we take the coefficients and put them in a vector and take the tensor product with the identity matrix. So for example, let's just say that the basis we want to perform is the monomial basis. So clearly, only C0 here would be equal to 1, everything else is equal to 0. And the x here would then be 0, 0, 0, 0, 1, which we have actually seen for the matrix, for the Mandelbrot case, where Rn is equal to zeros and then 1 at the end. So that's just an example of it working. And then we have our y, which is the 1, and 0, 0, 0, 0 as a column vector, which we've also kind of seen in the Mandelbrot case, which is the scalar case, but now we are taking the tensor product and essentially, it would be a block of zeros and then the identity matrix for of 0. So we're introducing a change of base matrix, which we're going to call big phi, and it has the last rows of its inverse, coefficients of 1. So essentially, we've seen this form before, the resultant form, and we are introducing 2 univariate matrices, which we'll be treating. So there is a similarity transform that we can use, saying that if this one is equal to this one, then we say that they're similar. With that said, we're using these kind of as like a change of basis to help us change bases. And here, if we do a bit of math, then we end up with x times big phi inverse times the change of base, linearization, and times e inverse times y. And here, this you can find in our forthcoming paper. I'm not going to talk about this too much here. All right, so now moving on the last topic, and we're pretty much going right on time. So we all learn in numerical methods, any course that we take, that an algorithm is called numerically stable if it's guaranteed to produce an exact result to a nearby problem. I've talked about this for the Euclid polynomial case, so now we're applying it to matrix polynomial case. So in the context, we are perturbing our matrix A, and we are perturbing our matrix B, and we can essentially find the solutions to this as what we have seen for the perturbations that I showed earlier. I'll show more examples later. And so I just want to note, usually when we're solving matrix polynomials, we use the QR algorithms or the QZ algorithms, and they are typically, or they are numerically stable. So, as we mentioned that a numerically stable problem is the exact solution to a nearby problem, we can actually use this to our advantage and calculate what we call a condition number. So this is the relationship between backward error and forward error. So in this case, for eigenvalue problems, we have this, our C here is our condition number. So the generalized backward stability for a polynomial eigenvalue problem has been done before, and we can see that it is the perturbed matrix polynomial, and we are trying to solve for that particular perturbation. And this just notes that the perturbations that are taking place are smaller or equal to epsilon here. So this is just the explicit form where we have p of lambda times x, which is our exact eigenvalue problem. We're taking the 2 norm of that, and we can notice that this part within the brackets here is our condition number multiplied by our x. So just to be clear, this is for the matrix polynomial case, not the linearization. All right, so here we can do the left eigenpair, the normalized backward error for left eigenpair, and we can see that this is very similar to this, but instead we are using the left eigenpair. Also, it's the condition number here, but here we have y instead of x. So now we're dealing with the backward stability of the linearization and not the matrix polynomial. So if we let L of lambda times lambda x minus y to be the linearization of P of lambda, the backward errors of the left and right eigenpairs are given as follows. So we can see that it's pretty similar. So we have our left eigenvalue times our linearization. This is what we call our condition number, and we are taking the norm of our vectors. Okay, so here for simple eigenvalues, we have our condition numbers. There are many proofs for this. This is really well known. And for pseudospectra, we can define it very similarly to the scalar polynomial case. So again, we are perturbing our matrix polynomial times our right eigenvector equals 0. And again, we're restricting the perturbation. And the generalized pseudospectrum introduce weights. So in this case, in my talk, I'm just going to say that the weights for the monomial cases are equal to 1, and then we have to change the weights if we're changing the polynomial basis. So here we have a theorem from Rob's former PhD student, Amir, and they talk about the pseudospectrum of P, and it doesn't necessarily need to be expressed in the monomial basis. So here we see that this is our condition number, and our condition number includes anything that, any polynomial basis. Okay, so just a remark here, pseudospectral connection between backward error and conditioning. So in the previous slides, we will notice that the definitions are pretty similar. So we always are perturbing our matrix polynomial times our right eigenvector equals 0. So here, what we're doing is using pseudospectra to our advantage to look into our backward error and our conditioning. So here is the connection to backward stability. I mentioned it very briefly just now. So again, here's our definition of our normalized backward error. And because the backward error for an approximate eigenvalues can be written as the minimum of this, and therefore we can see that the E pseudospectra can be expressed in terms of backward error. So the backward error is very similar to pseudospectra. So let's show this by example. So our first example, we have a singular leading coefficient. So if we multiply these two together, we can see that since this is a singular matrix, that causes the whole, the product of these two to be singular as well. So we have these values here, and we can take a look at the pseudospectrum. So on the left is using the algebraic linearization, whereas in this case, we're using the Frobenius linearization. And we can see that our linearization is much more backward stable, or suggests that it's more backward stable, clearly because we can see the difference between how closely wrapped all of these ones are, for example, compared to this one. So we can see that even, so numbers, so blue is really small, red is really large. So we can see that all of this here are blue, meaning that we're only performing a very small perturbation, and yet here, for example, we're getting a solution that is far off from the exact solution. Whereas in this case, we can see that despite us perturbing it a large amount, for example, here is still fairly or relatively close compared to over there. So we can also show you that this works for the Bernstein basis. So this one is our Bernstein basis. So N here is the degree So the superscript is our degree, and our subscript is the index. So again, we can perform our algebraic linearization, and we can perform a Frobenius linearization. But we actually did one more. So this one's algebraic linearization. This one is the linearization expressed in the Bernstein basis. And in this one, we have converted our matrix polynomial, so it's expressed in the binomial basis, and performed the Frobenius linearization for that. So here we can see that the pictures that we get are quite different. So here again, blue means very small perturbation, red means very large perturbations. And we can see that here, it's quite good in terms of here and here. In this case, we can see it's not as good as this one, but it's okay. Some of the eigenvalues we can see that are still tightly wrapped together, whereas for this one, it's also evident, but we can see that this particular parts are not as good because you cannot distinctly see the three eigenvalues or the multiple eigenvalues that would reside in that part. All right, so lastly, our last example here, we've already talked about the contours, but what are these black dots? So these black dots are explicit perturbations. What that means is that we perturb our problems and compute the eigenvalues, and we plot them here. So the black dots here, we perturbed it 0.05, and we can see that all of the results falls within our contour here. And we can do the same, so this is algebraic linearization, and this for Frobenius, we can see that this is similar. So just judging from the black dots here, we can see that this is not as well conditioned as this one, because the region that the black dots are in are much larger. Okay, so we're almost there, concluding remarks. So in this talk, we talked about the historical developments from when Peirce started and using Mandelbrot matrices, and we're generalizing them, applying them to equal polynomials, and extending it to matrix polynomial cases. So at this point, the ideal of minimal height companion becomes clear from our experimental results. And we can study numerical stability and continue studying numerical stability for the matrix polynomial case. So for future work, what we want to do is combine homotopy methods and the singularity detection in an attempt to create something what we call a divide and conquer algorithm. So for us to be able to kind of navigate our way through the singularities would help a lot. In my master's thesis, I did both companion matrices and homotopy methods, and we can see that homotopy methods can find the roots much quicker. But then once we get to really large degrees, it gets really complicated because the singularities get really close and it's hard to navigate through all of the singularities. Here just outlines all the steps that we would take, and hopefully we can tie it into more Bohemian matrices. Or just Bohemians, we've changed the terminology now. All right, thank you so much for listening.
Okay, so at this point, I open the floor to non-examiners for questions. Fran has said that the live stream is working, so
Perfect.
she's been attending, so this is good. But so questions from the non-examiners. Greg?
Was really nice talk,
Oh, thank you.
I think. And so there's some religious thing in your talk. Absent a miracle, it's on page 45. It's around about slide 45. Yes, that's that one.
Yeah.
Yeah, and what do you mean by that, so more precisely?
Okay, so what we mean by that is if our algorithm or how we calculate roots, if it's not well conditioned, obviously our result after or using it is not going to be good, right? So it cannot miraculously be well conditioned, the eigenvalues. Does that make sense?
Oh, okay.
Any more questions? Tyler?
Can you- I don't know if I missed the definition, but can you explain what you mean by height?
Oh, yes.
Like, I'm very confused. What you
Oh,
mean by
height? What we mean by height, so let's just take this one.
Sure.
So what we mean by height is the absolute values of the elements, and the largest one would be our height, essentially.
So for that one, it would be
So
Just
it'd be
all-
1.
okay.
Yeah. So,
So the polynomials.
right, okay. So if we use the Frobenius linearization, remember that we have to use the coefficients of these particular polynomials. So the largest value would be 10 in this case. Right, so when we're taking the condition number, it doesn't really matter what norm you're taking, but it is related to the elements in the matrix. So the larger the elements in the matrix, the larger the condition number could potentially be.
And it's not obvious from the first four, the size of these coefficients grows doubly exponentially in the end, or exponentially in the degree. And so having something grow exponentially in the degree versus flat.
Because we can see even just from this, the size, or sorry, the height of these elements never increases.
More questions? Then let's thank Eunice again. And now we will stop the live stream and move the exam into the exam room and start the Zoom.
Did you realize that the display on that computer there is all backwards?
Yeah. It is, but then when you stream it out, I think it flips back. So when you see it, it's
Good. Yeah.
I'm just gonna grab it from the top.
Yeah, sounds like it. Yes, we have time. I'll go and talk to Ricardo